This lesson is on simplifying exponential expressions. This basically means we're going to be reorganizing products of numbers and variables into simpler formats. Let's first take a look at what an exponent is. Exponents allow us to write multiplication in a shorter form. For example, if you had 2 to the power of 3, that tells you to multiply 2 by itself 3 times. Analogously, you could be looking at multiplication, 2 times 3, as an addition statement of 2 plus 2 plus 2. Notice it's similar, where multiplication is a form of repeated addition and exponents are a form of repeated multiplication. Let's look at some definitions here. When you have a power with an exponent, n is the exponent. The exponent tells you the number of times you're going to multiply the base. X is the base. Let's first take a look at what happens when we multiply powers. In this case, we have x squared, which is x times x, and x cubed, which is x times x times x. That gives us a total of 5 x's being multiplied, which also can be written as x to the power of 5. That's one way of rewriting x to the power of 5. Notice what happened with your exponents when you were multiplying powers with the same base. 2 and 3 added to give you 5. So in general, you may find that when you multiply powers with the same base, you're actually adding the exponents together. Let's take a look at some more examples of that. So 2 to the power 3 times 2 to the power 4. We've got the same base. So this actually just means that 2 times 2 times 2 is multiplied by 2 times 2 times 2 times 2. Rather than writing all of that out, you can imagine it and follow the rule of adding the exponents when the bases are the same. That gives us 2 to the power of 7. This is a simpler way of writing it, and it's easier to calculate as well. Let's take a look at the next example. In the next example, we have different bases. Remember that when you have no symbols in between components, they are all multiplication. Multiplication can be written in any order. And specifically, I want to rewrite these in an order so that like bases are written side by side, because we can only combine and simplify when the bases are the same. So we've got a to the power 3 times a to the power of 2 gives us a to the power of 5. And then we also have b to the power of 5 times b to the power of 7, giving us b to the power of 12. We can also look at this example here. Bases are the same, so we can just follow the rule of adding the exponents when we are multiplying the powers, giving us x to the power of 5a. Let's take a look at what happens when we divide powers. Here's an example, taking x to the power of 5 divided by x to the power of 2. That's 5x is being multiplied up top over 2x is being multiplied in the bottom. Remember that every time you have the same number divided by itself, it gives us 1. It simplifies. So we have this one simplified with this one, simplified, simplified. So really, 2 of them were the same, leaving us with 3 on top. So what happened with our exponents? When we divided, our exponents subtracted. And here is the rule for that. X to the m over x to the n. Quotient leaves you with a subtraction of exponents. Here are some examples. Remember, the base has to be exactly the same. So since both of these bases are -3 in a bracket, we can use the following rule and say we're taking -3 to the 17 minus 9. And 17 minus 9 gives us 8. So we've got -3 to the power of 8. And that is the simplest form. You can leave it like that. You can evaluate if they ask you to. In the next example, we have two different types of bases here. We've got an A and a B, and remember also that when you have no exponent, there is an exponent of 1, because when you take something to the power of 1, it stays the same. So here, we could separate this to a to the 8 over a to the 1 times b to the 11 over b to the 6. This is a preliminary step to kind of show you. You can sort of skip this step if you feel comfortable enough. You can also skip this step too, but take a look at what's happening when you divide. One of these a's will cancel, giving you 7 a's left up top, which was found by taking 8 minus 1. And similarly, the b can be found by taking 11 minus 6, giving us a to the 7 times b to the 5th. And that's a little bit of a cleaner format than the original. Let's take a look at what happens when we take powers of powers. So in this case, we are squaring this bracket. That means we're going to multiply it by itself twice. Within that means within each one we'll have 3 x's being multiplied together. So essentially what we have here is a description of 2 groups of 3 x's all multiplied together, which gives us 6 x's all multiplied together, which can be seen as a product of exponents. So when you take a power of a power, you're actually multiplying the exponents together. Here are some examples of that. All you need to do here, now that you know the rule, is go 5 to the 3 times 5, which is 5 to the power of 15. If you really want to convince yourself, you can see that this is 5 to the 3 to the power of 5, meaning 5 groups of 3 5s in each one. And keep going, you'll see that's 5 times 3 5s altogether, 15 5s altogether. Here's another one. Now, it kind of looks like it could have 2 bases, but it's the same base. But let's do step by step here. So let's complete this part first. So we've got y to the power of 3 times 7, which is 21, times y to the power of 2 times 11, which is 22. Now we can use the product rule from before and add up our exponents. 21 plus 22 gives us 43. Here's another example. What if you're taking a power of a product of different bases? Well, let's take a look. That would mean we're going to square, by definition, square that bracket, multiply it by itself. We can rearrange that, and that really means everything is being multiplied. Multiplication is commutative, so x's could be multiplied first and y's afterwards, which really means you're squaring the x and squaring the y. Essentially, whatever components you have will be taken to that particular exponent. In general, when you have 2 different bases, or even more bases, you can extend it to however many you want, the exponent will attach itself, will take each term to a power. So to better illustrate that, let's take a look at some examples. In this case, we have -5 times x in the bracket, and each of those components are being squared. So this would be using this rule, which would mean -5 squared in a bracket gives us 25, and x squared is x squared. If you want to convince yourself, you could actually write it out and say, well, negative 5 squared is negative 5x times negative 5x, which gives us negative times negative, giving us positive 25x times x squared. Let's try this rule on this next example. Here we have these components. We have negative 2, a to the 4, and b. Notice I'm just separating them so that I know what all my things are. They're all being multiplied together. However, this bracket is being multiplied together 3 times. Therefore, each of these will be multiplied by themselves 3 times. So we can rearrange them in our heads and rewrite them in this manner. Negative 2 to the power of 3 is negative 2 times negative 2 times negative 2, which gives you negative 8. Then you have a to the power of 4, so you have 3 groups of 4a's each, which is 12, and 3 groups of 1b each, which is 3. Similarly, we can look at powers of quotients. So when you have fractions and you multiply them by themselves, you really end up multiplying all the top numbers and all the bottom numbers, which results in squaring the numerator and squaring the denominator, giving us this rule. A fraction to a power really takes each component, the numerator and the denominator, to the same power. Some examples of that would be taking the following: 2 squared over a and cubing it. Well, really, you could write out 2 squared over a times itself 3 times, but you would see that 2 squared would be multiplied by itself 3 times, and a would be multiplied by itself 3 times as well. So we might as well use exponents to notate it a little more efficiently. This gives us 2 to the power of, and the rule tells us to go 2 times 3, and the reasoning is we've got 3 groups of 2 2's each, meaning 3 groups of 2 is 6 groups of 2's. And then we've got a cubed on the bottom. And that's it. Let's take a look at this next one. This negative is kind of hanging out in front. You'll notice that when you square a negative, it becomes positive. You could just keep it at that, and then notice that you're going to square the numerator and the denominator. You could also take the negative and stick it to either the denominator or the numerator, but only picking one of them. So in this case, you could say that that's a negative 3a cubed over 2b to the 4, and we are squaring the numerator and the denominator. If you're squaring the numerator and it's a product, we need to separate each component and square them both. Similarly in the bottom. So really, you're almost like distributing your exponent. However, a very common error here is to start getting used to multiplication of exponents and apply that to the actual numbers. Remember, the big numbers, not the little numbers, are still regular numbers. So if you're taking 3 to the power of 2, that's going to be 9, negative 3 to the power of 2. You'll notice that you'll start getting used to going 3 times 2 because it's so easy to just go 3 times 2 here because you've got 2 groups of 3, which is 6. Oops. 2 groups of 3, which is a to the power of 6. So it's very important that you remember that you're not multiplying this 2 and 3, but you are multiplying this 2 and 3. So really be careful as to which rules you're using when. When you have exponents, you're going to be following the rules that we've been outlining in this lesson. When you have an actual big number, it's as before. Just want to point that out because it's a very common error to make this a 6. Okay, and here we've got 2 squared, which is 4, and b to the power of 4 to the power of 2, which is 8, b to the 8. All right, now let's look at rearranging 1. How could we rewrite 1? Well, we could write it as anything over itself, as a fraction. You'll notice that means we're taking x to the power of 1 over x to the power of 1, for example, which means x to the power of 1 minus 1, which means x to the power of 0. So wouldn't that mean that any time we take anything to the power of 0, we should get 1? Well, yes, that is correct, as long as that anything is not 0, because remember, we cannot divide by 0. You can't have 0 over 0 equaling 1, but you can have anything else. So our rule for this example is that anything to the power of 0 is equal to 1, as long as your x is not 0. Also, taking 0 to the power of 0 wouldn't make any sense, because 0 times something is usually 0, whereas anything to the power of 0 should be 1. Therefore, it's a contradiction and does not make sense. If you type that into your calculator, you will get an error. So let's take a look at a few examples using 0 within our exponents. If you have something to the power of 0, it doesn't matter what this something is, as long as it's not 0 itself. It's going to be 1. Bam, done. You could have anything. Complicated, 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 but not 0, equal to 1. However, let's take a look at this example. This 0 exponent is only applying to the x, meaning the 5 is still hanging out. So this is a times sign, and this component equals 1. Therefore, it's 5 times 1. Therefore, it's just a 5. Now here, this should be 1. However, what's x minus x? No matter what x is, x minus x is going to be 0 to the power of 0, and that does not make sense. It is undefined. Another interesting form of exponents are negative exponents. So let's take a look at this example. 1 can be rewritten as x to the power of 0, and x squared can still be written as x squared. Now we know from the quotient rule, we can subtract exponents with the same base, so that would give us 0 minus 2, which would imply that x to the negative 2 should equal 1 over x squared. Therefore, here's a very important rule that will be very useful in your simplifications of negative exponents, mainly because we never want to leave our answer with negative exponents. So we can use the rule of converting a negative exponent to its reciprocal with a positive exponent. So you'll notice let's take a look at a few examples of that. If you have negative 2 to the power of negative 3, the negative exponent here tells you that you can rewrite it as 1 over negative 2 to the power of 3. Now, a negative 2 times a negative 2 times a negative 2 gives us still a negative, but an 8. And that's simplified form. In this case, you have a negative hanging out front, so that's not going to move. This negative exponent sends this guy to the basement. Negative exponents are bad got to send them down to the basement to become positive. It's just a story. Negative 1 over negative 2 squared would be negative 2 times negative 2, 1 over 4. Another one complete. Now this one, the negative 2 exponent is only applying to the x. So the negative 2 is still hanging out, and it's multiplied by 1 over x to the 2, which means the 2 is over a 1, because whole numbers are over 1. So it stays up top as negative 2 over x squared. So all of these answers do not have any negative exponents, and therefore they are a fully simplified form. One more note about this is that you'll notice that when you have a negative exponent, it's been bringing it down. So therefore, if you have a negative exponent in the basement or in the denominator, that would actually bring it back up. The proof of that would be 1 over x to the negative n, giving us 1 over x to the n. Remember, when you're dividing by a fraction, you're actually multiplying by its reciprocal, which brings it back up. So a negative in the denominator will bring it up as a positive. So that's the alternate format of this rule. Let's take a look at a few more examples. Here you've got a negative exponent, can't leave it like that. So we're going to mix a few rules here. We're going to want to apply the product rule. So negative 2 to the power of negative 2 and times x to the power of negative 2, giving us 1 over negative 2 to the power of 2 times 1 over x to the power of 2 using the negative exponent rule, which gives us 1 over negative 2 squared is 1 over 4 times 1 over x squared, giving us 1 times 1 is 1 over 4x squared. Notice that you might have completed this question differently. Your approach might have been different. Your order of rules might have been different, but you should still get to this. So if you completed it in a different way, do not worry about it. That is perfectly fine. An alternate way, you could have applied the negative exponent first, giving you 1 over negative 2x squared. And then squaring each of those, resulting in 1 over 4x squared, which is almost simpler. Sometimes certain ways are simpler, and it's difficult to choose which to apply first. It really just comes with practice. Here, we've got the same base. So since we've got the same base, let's combine our exponents if we can. So same base, product rule, you want to add your exponents, negative 4n plus 3n, which gives you negative 4n plus 3n is negative 1n. Oh, now we've got a negative exponent. Can't leave it like that. So let's use our negative exponent rule, which means going 1 over z to the power of n. And that can be a simplified final answer. Let's take a look at a little bit bigger of an example. Here, we've got an outside exponent, we've got products, we've got more negative exponents inside. Man, there is so much possibility here of simplification. So remember, when you're trying this on your own, you could take one of many approaches. You could simplify inside first, you could spread out this negative exponent, you could use the negative exponent and reciprocate all your numbers or letters. You have many, many options. My rule of thumb, for the most part, is to simplify what's inside first. However, you might be successful doing it other ways as well. So let's try simplifying the inside first. So this is going to stay. The 2 is still in the numerator. If it had a negative exponent, you might want to put it into the other level. Like say this was 2 to the power of -1, then that would be a 2 to the power of 1 in the bottom. But that's not the case at this point. So let's move on. So the 2 stays. Then we've got a to the power of -3 minus 1. This is a 1, and this is a division here of the a's. And because we're taking the quotient rule, we're subtracting the exponents. And then b is to the power of 1 minus -1. All right, let's take the inside further. That gives us 2a to the power of -4, b to the power of 1 plus 1, which is 2. Okay, so we still have a negative exponent here, but that's okay. Let's just maybe input this guy now. So 2 to the power of -2, a to the -4 to the power of -2, and b to the power of 2 to the -2. Okay, 2 to the power of -2. Well, before we can take 2 to the power of 2, we have to deal with this negative, which takes it to the basement. 1 over 2 to the power of 2 becomes positive in the basement, which is actually a 1/4. It's interesting. I don't think you've ever considered writing 1/4 as 2 to the power of -2, have you? Let's move on. This is all multiplication. This is a to the -4 to the power of -2. When you take something to the power of something else, you're multiplying your exponents. So we've got -4 times -2, which is +8. And times b to the 2 times -2 is -4. Let's simplify that, put it all together. The a to the 8 is in the numerator. The 4 is in the denominator. And this guy here, b to the -4, if it stayed up top, it would still have a negative exponent. So remember, the negative exponent can be eliminated by changing its level. So this actually means reciprocate this in order to keep a positive exponent. So it would go to the basement with a positive exponent of 4. If you would like to see more of these complicated examples, please ask in class and we will go through some more of these. Also, try out using different rules first. You'll notice that you'll be able to get to the same ending in different ways.